everyone in this picture is thinking of the exact same number. One of them is thinking of it in its decimal representation, which is base 10. Decimals are another of those elephants in the room. If I ask you to think of real numbers, there's a good chance you'll think of decimals, which is certainly reasonable. But why should we think of base 10? Real numbers are much more universal than our 10-finger system, and decimals obscure a lot of what the real numbers are really about. What appears on the screen here is a statement which tests whether you really understand how decimals represent real numbers. The number 1 has a couple of decimal representations. One of them, on the left, is 0.99999 repeating forever. If you don't believe or understand this equality, then you don't understand one of the prerequisites for a calculus course. And yet, it is not until the second semester of calculus that we typically explain this equality, because the statement expresses 1 as a sum of an infinite series. Every decimal expansion is an infinite series, but we don't talk about this until the second semester of calculus. And yet students coming into calculus are already supposed to understand the real numbers. Are we putting the cart before the horse in our curriculum? But I'm not going right back to the axioms of the real numbers yet. Again, for pedagogical reasons, let's try to stay rooted in the familiar. You probably remember that every repeating decimal expansion represents a rational number. That is an if and only if statement. Every rational number has a repeating decimal expansion, and conversely, every repeating decimal expansion specifies a real number. Why and how? Let's take the easier direction. Every repeating decimal expansion specifies a rational number. Now here we have not a proof, but an example. At least from this example, you can see how the general case should work. We take an example where the decimal expansion of A repeats every third digit in its decimal expansion. Write down also 1000A, which has the same repeating digits as A after the decimal point. And then subtract, like this, so that the fractional part, all those decimal places after the decimal point, will cancel. We get 999 times A equals 5130. And so A is 5130 over 999, which equals 190 over 37. That is a rational number. And essentially every repeating decimal can be expressed as a rational number using this same method. The converse, that every rational number has a repeating decimal expansion, requires a little more work, and I'm not going to take time to discuss that here. My point is that if you accept this argument, and most students do, then we can use the same argument for our repeating decimal 0.99999 repeating forever, because you multiply by 10 and then subtract to get 9A equals 9, which means that A equals 1. We just proved that 0.9999 repeating forever equals 1. Now at this point, I usually get mixed reactions from students. Some students believe this argument without any problem. Some students have qualms about it, but their concerns have been squelched by years of teachers talking them down, forcing them to be quiet about their misgivings. Personally, I believe this argument requires some discussion. If you don't really believe this argument in your heart of hearts, then the rest of our semester is really kind of pointless. In class, I usually try to have students vote on how many actually believe the argument given, and to encourage students to verbalize their objections. Please pause the video now and contemplate this. Do you accept this as a valid proof? What are your objections? Over the years, I've had many discussions, including one very heated discussion from a student who kept me for about 2 hours after class one day, venting his fury at this argument, although I was mostly just listening. Over the years, I've heard many concerns from students, many of them valid, and I hope you'll be able to articulate your concerns to me. Being skeptical is a necessary trait of any good mathematician. So assuming you've had time to think about this, now let me summarize some of the concerns I have heard from students. Later, I'll tell you my own concerns, maybe, about the argument. One skeptic complains that when I write down 10 times a, I stuck an extra 9 at the end before subtracting. Is that really fair? And I respond by saying that the ... means an infinite list of 9s. If we had only a finite list of 9s after the decimal point, this step would not work, and we would have then a number strictly less than 1. It's only by having an infinite list of digits of 9s after the decimal point that I can make this conclusion: my number is actually equal to 1. Of course, my skeptical student may not accept that it is possible to have infinitely many 9s after the decimal point. A student might feel that only finitely many digits should be allowed. But by that reasoning, it seems you're denying that a number like pi exists. Or, worse still, what about 1/3? That has an infinite number of 3s after the decimal point, right? Another skeptical response is that 0.9999, repeating forever, can't really equal 1 because it looks a teeny bit smaller, and so it's a little bit less. Probably very close to 1, even infinitely close to 1. Now, this response does not actually identify any hole in our proof. It just says that regardless of whatever proof we put forward, the student is not willing to be convinced, probably based on their own intuition about the real numbers. Now, I want to voice some sympathy for that point of view. There is a justified intuition about numbers being infinitely close, and this intuition had a part in the historical development of calculus. My response, however, here is that there is a number system very similar to the reals, namely the hyperreals, in which numbers can be infinitely close. That intuition is perfectly reasonable. However, that intuition does not apply to the real number system. If you're thinking about any number system where numbers are possibly infinitely close, then you must be talking about something different than what we're talking about here with the reals. Our conflict then becomes less a question about the value of a number, more about clarifying our choice of the number system that we're in. Now, here is an important analogy. We could argue till kingdom come about whether a professional sports team should have 5 players or 9 players. If you're thinking about basketball, while I'm thinking about baseball, we'll forever disagree. Basketball and baseball are just 2 different games. Neither one of them is more valid than the other. If a player carries the ball and you cry foul and I cry safe, who is right? The answer depends on which game we're talking about. And here is the revelation. There are many kinds of mathematics, like real analysis or hyperreal analysis, each with its own rules or axioms, no one more correct than any other. Within each game, we have valid and invalid arguments, depending on the rules of that particular game. And outside of that game, there is no way to call any move legal or illegal. If you are imagining a number system with numbers that are infinitely close, then there might be a set of rules where that is valid and even reasonable. But I'll tell you, that's not the real number system. By the way, we're not taking time here to discuss the foundations of the hyperreals. That's much too involved for us. So let's just put that discussion away for now. Here is a third skeptical response to my proof. Make up your mind. You said A was 1. Now you're saying it's something different. 0.9999 repeating forever. Which is it? Make up your mind. And again, this response doesn't point to any particular hole in my proof. It's a response based on a faulty assumption that each real number has its own decimal expansion, one and only one way to expand it as a decimal. And we imply this every time we say the decimal expansion of a number, when in fact this is misleading. There are numbers that have more than one decimal expansion. I just pointed that out with the number 1. which has, in fact, 2 decimal expansions. And there are many real numbers, in fact, infinitely many, but not all real numbers, which can be expanded as a decimal in more than one way. So there's a misconception here which gives rise to this skeptical response. I recently heard that a proof is an argument that compels belief. If that's true, and if my proof did not convince you, then because of the importance of this point for understanding the real number system, then rather just shouting down all the skeptical responses, I think it's worth having on hand a few other alternative proofs. That 0.9999 repeating forever equals 1. Here is one proof that I like. Most students will agree that the decimal expansion of 1/3 is 0.3333 repeating forever. And I mean the expansion because there's only one in this case. So if I write this down again, and then again, and then I add up, I get that 1 equals 0.9999 repeating forever. What I like about this proof is that it counters some of the concerns of skeptic number 3, because here we started with a number, namely 1/3, for which the decimal expansion is unique. I haven't heard any student quibble about this point. And here is a third proof that I like a lot, and which I offer to skeptic number 2, who really believes that 0.99999 repeating forever is just slightly less than 1, infinitely close but not equal. If these two numbers had a gap between them, presumably a being less than 1, and there's a gap, then you should consider their average, the average of a and 1. So if you have a gap between the two numbers, the average should be exactly halfway in between. So what is this average? Let's work out its decimal expansion. And you can do this using decimal arithmetic. I get 1.9999 repeating forever divided by 2, and by longhand division, that comes out as 0.99999 repeating forever. So the average of a and 1 is the number a that we started with. Now, how can the average of a and 1 be exactly a? If a is less than 1, then we'd expect the average to be something bigger than a, not equal to a. The answer, evidently, is that the numbers a and 1 must actually be equal. Now, we don't really need more than one proof. One proof should be good enough, but sometimes in order to convince a skeptic, it's useful to have others. For any students of mine who end up teaching math in the future, I think this is a point worth discussing now, and I'll encourage you to listen patiently to your students' thoughts on this question. Applaud your students for their healthy skepticism. Don't put them down for their ignorance. Many of their complaints are based on misunderstanding of what the rules of the game are. You cannot blame students for playing basketball when you're playing baseball, at least if they've never seen the rules, especially since our pedagogical approach does not start with the formal rules, right? We're doing by example. We expect students to pick up on the rules by imitation, following our lead. Until they get to college, maybe then they get to see the actual foundations for themselves. Now, to resolve a question in many minds, let's point out that most real numbers do have a unique decimal expansion. Here are a couple of examples of real numbers, which are typical in the sense that each has one and only one decimal expansion. Here is a rather arbitrary choice of real number, which has 2 different decimal expansions. In the first expansion, we don't really consider 0.14 any different from 0.140 or 0.140000, or even listing all the zeros at the end. There are always infinitely many zeros there, regardless of how many you explicitly write down. But the second expansion, 0.1399999 repeating forever, that one I would consider the second expansion, different from the first. These are just 2 of many examples, infinitely many examples, of real numbers having 2 different decimal expansions. Which real numbers have this property? Precisely, they are all the rational numbers which have a reduced form in which the denominator is a power of 2 times a power of 5. So this description is an accidental consequence of the choice of base 10 representation of real numbers. It carries no true significance for the study of real numbers. So it's more evidence that decimals provide a misleading impression of what the real numbers are really about. Okay, so what exactly are the real numbers? How do we define them? And how can we prove theorems about the real numbers? And these two questions are related because however you define the real numbers, that will provide the basic ammunition you need to prove theorems about the real numbers. We aren't yet ready to define precisely what the real numbers are. We start by saying a few more things that the real numbers are not. First of all, we cannot define the real numbers using decimals. For one thing, the real number system is a natural concept which transcends the fact that we have 10 fingers. The real numbers are much more universal than that. Secondly, it would be circular to try to define the real numbers using decimals. I'll take it as a given that understanding of how decimals work is based on Calc 2, understanding of infinite series, all of which is grounded in a prior understanding of the real numbers. How do you avoid the logical fallacy here of circular reasoning? Thirdly, if your definition of real numbers is in terms of decimal expansions, then that is what you must use in order to prove anything about the real numbers. But then it would be hopeless to prove anything. For example, pi. Pi is a pretty important number. What do you really know about its decimal expansion? It looks pretty random, but can you say anything for sure about its decimal expansion? Does it contain infinitely many threes in the decimal expansion? Nobody knows. Nobody. Yes, pi is irrational, and you can prove that, but you cannot prove it by looking at its decimal expansion, because so little is known about the decimal expansion. Fortunately, our definition of rational does not refer to decimal expansions. Otherwise, you'd be stuck trying to prove something as simple as pi is irrational. Rather, the fact that the decimal digits of pi don't repeat forever is a consequence of something more fundamental. The fact that the decimal digits don't repeat forever is a curious consequence of the fact that pi is irrational. In fact, almost nothing about the real numbers are proved or can be proved using decimal expansions, or for that matter, any base of representation. Even something as basic as the distributive law. If you were to try to prove the distributive law using decimal expansions, it would be about the most ugly technical thing I'd ever seen. In fact, I've never seen a proof this way. I doubt that anybody has ever tried because there are much better ways to do it, avoiding decimals. If decimal expansions are not the answer for defining the real numbers, what is? How about saying that real numbers are just points on some ideal number line? So we have a problem here because whose idea of a number line are we talking about? People actually have different ideas about what a line really is. You might think that a physical line provides some kind of absolute standard, but it does not. As I said in my first video, physical quantities are not the same thing as real numbers. But that's fortunate because if real numbers were defined using physical quantities, then the best we could come to proving a theorem about real numbers would be to do a measurement, a physical experiment. And that's not a genuine proof. If you wanted to prove that pi was between 3.14159 and 3.1416, you'd have to do a measurement on a large circle. But you cannot find any measuring device accurate enough to do that kind of measurement. Another example you can prove mathematically, right? For any three distinct real numbers ABC, exactly one of them lies between the other two. Think about this fact. It should sound very reasonable. I gave you the axioms for an ordered field in the first video, and that gives you enough of a basis to write down a short proof of this result. However, you cannot prove it by physical experiment. In fact, it's not even true in the physical world. You imagine it perhaps to be true. You have some physical experience, which, however, does not account for cases where ABC are extremely large or extremely small. And it's in these cases that the whole fact so-called fact breaks down anyway on physical lines. So that's part of the weirdness of the physical universe. I'll say more about that in future videos, and we'll talk about the weirdness of the ideal mathematical line modeled by the real numbers. A third attempt to define real numbers is to say that we're starting with the rationals and then filling in the gaps. Great, what does that mean? Well, it's closer to the truth maybe, but it's still not precise. It certainly requires refinement. The statement has more than one possible interpretation, and it still isn't something precise enough that it can be used in a proof. In particular, it is possible to imagine the rational numbers lying in a line with gaps between, and the real numbers squeezed in between those gaps, but then you would still have gaps between the real numbers, and hyperreal numbers filling in those gaps. Or not quite, because then there are still gaps between the hyperreals. And then you need a bigger and bigger number system to fill in gaps further and further. There's not really a limit to this process, unless you might want to think of the surreal numbers as kind of a limit to this filling in the gap process. But the surreal numbers are such a huge thing that it's not even strictly a set. It's something that we'll talk about later as an example of a proper class, or maybe not even mention at all. Having listed about 3 different things that provide some partial insight into the real numbers, but which fall short of providing an actual definition, are we any closer to saying how the real numbers actually are defined? Well, we have said that the real numbers are an ordered field in our first video. Over the course of a few lectures, we'll say more. The real numbers are a complete ordered field, having the rational numbers as a dense subfield. And then that pretty much nails it down. There are several waypoints on the road to get to there, so it'll take us a few lectures still to be able to say what we mean by all that. And once we've clarified what these defining properties are, we'll be able to take them as axioms for the real numbers. The axioms we have for ordered fields describe more than one possible number system. We have lots of ordered fields, the reals, the rationals, q of root 2, and hyperreals, among others, as examples of ordered fields. We're shooting for a list of axioms that are categorical in the sense that the real numbers, and only the real numbers, can satisfy our ultimate list of axioms. That's a doable task, but it'll take a few lectures to get there. Now, I point out that our definition of the real numbers depends on an elaborate foundation. We usually start with the natural numbers, build up the integers from there the rational numbers, and then the real numbers. In order to define the reals, we rely on a thorough understanding of the rationals, because we need to start somewhere. Each of our basic number systems is constructed based on something more basic. Even the definition of the natural numbers, they're based on set theory and logic. So nothing in mathematics proceeds from nothing. Everything relies on some kind of foundations, some kind of assumptions. We make no apology for this. Making assumptions is the only way to even get started.